Eu queria chamar para compor a mesa os professores Gerard Assayag, Moreno Andreata, o professor Jean Bresson, do ICANN. Eles vão estar presentes em todas as mesas. O professor Rafael Santos, da Faculdade de Engenharia Elétrica da Unicamp, o professor Adolfo Maia, do Unix, e o professor Stefan Schaub, que fez a palestra com a gente hoje. Tá bom, o Stefan me corrigiu que nós estamos 15 minutos atrasados, não? Ok. Por favor, gente, enquanto vocês sentam, I would like to explain how this round table might work. The idea is, most of the time when people go to a conference, they say that the best of the conference is when people sit and talk about something. And most of the time, they don't do that in public. We do that privately in a bar, maybe having meal, whatever, enjoying, and we discuss. So the proposal of this round table, it's very informal. We hope it works, okay? And I'm going to work as a mediator. That means we try to achieve a kind of dialogue, a kind of conversation between these people that are specialists, we have them here, and the subject that's open for discussion today. Let me be very precise about the theme. Sorry. Okay. The theme today is ferramentas computacionais para análise musical. Computational tools for musical analysis and creation. Okay? Sorry? Okay, yeah, of course. Stefan stressed me that if you have a question, you can send the question by the internet for us. Okay? We are keeping your questions. So, maybe we can start with a very, very, very brief introduction of this theme. I say that we have two people here that they are more specialists in mathematical tools and signal processing. That's Professor Rafael, Professor Adolfo. So maybe we start with them, give them 5 minutes to introduce some ideas, and after we can start with this dialogue between the ICANN team and the middle guy here that gave us the talk. So, but don't be shy. If you want to interrupt the other guy, say, no, I don't trust, I don't agree. I hope it works. And I'm going to sit here trying to articulate what should be articulated, whatever. Okay, we start. Adolfo, Rafael. Okay.
Okay. Good morning. Thank you for the invitation for this table. I'd like to think with you about the problem of intention in music. I think the problem of intention is everywhere in this discussion, in my opinion, because even if you put some stochastic distribution to produce something, you have some intention behind. So, and I'd like also to displace the discussion for the microcosmos of what you were saying today, the world of analysis. Because I particularly work on signal processing, and we try to discuss exactly how to produce sounds. So instead of talking about the world construction, the musical construction, we think about how to construct, how to build a sound. So that's a little bit what we are worried about. And so there are some concepts on doing this that touch me very closely. And one of them is the question of abstraction. I mean, the capacity of abstraction is a fundamental issue, in my opinion. You have to be able to to make some abstraction, to be able to have some intention. Otherwise, it's not possible. And that's I'll give an example. For example, a musician, if he thinks about a melody, something like this, he has to be able to preview, to predict what the intervals will be, to have an idea of what is his melody, things like this. So I'll try to be very, I'll summarize the main idea, because what is very important, let's take in parallel the classical approach on psychoacoustics. So what is important in psychoacoustics? The psychoacoustics parameters like pitch, loudness, duration, and timbre are very common. This is a common approach. And if you take the first three I cited, pitch, loudness, duration, you can see that they have three common properties that, in my opinion, are very important. They are predictable, they are unidimensional, and they are you can recognize them in very different situations. So I think these are three key properties: unidimensionality, to be recognizable, and to be predictable. So you can predict before doing a sound what is the interval. You can recognize an interval in many different situations, in many different instruments. So these three parameters, I think they are very important, and you can find them in pitch, you can find them in loudness, you can find them in duration. But you don't find them in timbre. Timbre is clearly multidimensional, not predictable, and everything, something. So I am, that's not original from me, but I think that we should not discuss timbre as a psychoacoustical parameter. In my opinion, timbre is the bag where we put everything we don't know, because sound is very complex. Actually, sound is not that complex, but the perception of sound is very complex. So everything we don't know, we put in this bag that we call timbre. So my question is, with the appearance of technology, what can this bring to us, in my opinion? Is exactly the possibility to take something out of this bag. That is, the question I would like for us to think is it possible to find other parameters different from pitch, different from loudness, that would have the same three properties I cited: predictability, to be recognizable, and unidimensional, in such a way that someone, a musician, would be able to make abstractions on these parameters, and so have different dimensions of creativity. That is the main point I'd like to put in this discussion. And together with this, some points that I think that could be interesting in this research. That's the point where I'm trying to go in. I think descriptors is a good point on to go forward in this research. And there is another point that I think it's very interesting. It's called stochastic resonance. Something that is very interesting, because I don't know if you know, all sensors, all human sensors are based somehow on this principle. Stochastic resonance means if you have a very weak signal, there is a way such that you introduce some noise on it, and the detection of this signal will be increasing. It's a little bit nonsense, that is. How can you introduce noise and it become more detectable? but actually is what happens in human ear and tactile sensors, and mainly, I think, all human sensors will have this. This is a very interesting issue because the perceptory system, the auditory system, is maybe the key to discover what could be these new parameters that could be that we could master them in the sense that we could, with convenient producing of sound, produce a sound that we to make something that we have intended to do. That's the main question. In the sense that the perception would be touched by this, and that would be a supplemental dimension for musical creation. That's the point. Thank you.
Very good. Thanks. Let's make two starting topics, Rafael and Adolfo, and after we open for, because I think we can also for people that's outside. So this is your time, Adolfo.
Let's take two statements and we. Okay. I have something very completely different from Rafael's speech. Let me say, I have talked with Asaya and Andreata, very good talk. And I would like to start with something like about the limits of the mathematical models and for composition and music activity in general. Let's just to talk with something that happened more than 15 years ago, and Jonathan was there in a bar with Professor Almeida Prado. He's a very important composer in Brazil, and we are in the in a table like that, and we are talking about his work named Carta Celestes, how to translate this, celestial chart, something like this. And I asked him, because celestial charts, you have a configuration of stars in the heavens. So I asked him, Almeida, how do you connect the position of stars and the constellations with the sound of you compose your piece? How can you measure the angles and the distance, something? And he said to me, oh, nothing about that. No, this way. How? Something like this. Andromeda. Oh, no, Sirius. So, and now we can analyze celestial charts in different ways, but the process of composition is completely different of any mathematical or formal analysis. So, what this can say to us? First, the composer does not have complete control about his own work. So other people can find different structures that is not thought by the composer. And this is very rich, in my opinion, very rich aspect of the human knowledge. So we can find different aspects of in the Einstein relativity theory, and so as music is something that is very objective and subjective also at the same time. So we are plenty of room to do everything we want. But it's necessary, in my point of view, to respect the limits of the math and the formal thinking in music. So we can use, like Stefan showed to us, study the formal structure or the math structure of Irma, but probably Xenakis as a very good composer, use his intuition also. So some connections is just aesthetic preference, no more than that. It's something very specific of Xenak style. It could be, for example, let me tell you something about Beethoven I got now. Leonora was an overture that have at least, we know, 3 different scores. This means that we can produce a lot of clones, if you wish, of just one work. So you can go to Irma and chant, for example, exactly the distribution of notes. And you obtain Irma 2, Irma 3, Irma 4, and you can say, you can do the same analysis for the Irma 1, 2, 3, 4, it doesn't matter. So what I mean, also, another analogy, and I end with this. For computers, there is a very general theory named Turing theory of computation. So what Turing did was to show that there are some problems in math or computer that are non-computable. So he, for example, to find some number, just to find some number, real number, in between 0 and 1, for example, there is a lot, infinite non-computable numbers. Impossible to get this number by a computer. It's impossible. He showed that's impossible. So we have some, what he did is that he shows there is a kind of limitation for the computer process. Also, perhaps that's my question. We have also a kind of limitation of the formal approach to music, and we cannot, in certain sense, what I mean that the human brain is far most intelligent than any computer process. Even if the computer process is constructed by a human brain. It's a kind of loop, but I think that you understood. And I think it's bad. It's okay. It's enough.
So I think after these 2 talks, we can stay forever for 10 days of discussion. But anyway, so it is open. Who wants to say something? That we have 2 points. If you don't mind, I'm going to resume. In one way, Rafael said that if you timbre and perception of time, but he said something about stochastic resonance. I think it's very striking that if you put noise on signal, somehow you increase the perceptibility detectability of the information. And another thing that, resuming what Adolf said, that even if you build the master of a computer with our brain, it's still below the the master of the construction, and then maybe give us also some constraints for musical analysis, whatever. So it's open. Who wants to say? Gerard?
Actually, we have experimented stochastic resonance when we were working on our machine listening tools that I talked about on Monday, but I didn't know it was called that way. I didn't know there was a theory. It's just something that we noticed empirically. So when we are doing machine listening for the improvisation tool, we are using spectral descriptors like Mel frequency, Capstral coefficients, or just Fourier transform, or just pitch following, with many techniques. And we had noticed that when we were working, for instance, on recordings, to extract the musical structure from recordings, from audio recordings, it was always better to start from bad recordings or old recordings with a very small bandwidth. Or even to artificially downgrade the quality of the recordings. So the way I didn't know. Now I will study. Now I will study the theory. That's very good. Thank you. But we had an intuition about this. We were trying to track inside the audio signal to recognize and to categorize units, meaningful audio and musical units, so segment the signal and then find relations between these units in order to detect the information, to detect the information and the structure of information inside the signal by connecting, as I showed with our graph and our factor record and all this formal technique, by connecting units in time which would have some similarity. And our intuition was that if there was too much information and detailed and precise information in the signal, that is, if the signal was really high quality, then we would have a hard job finding the categories, because we would have such a diversity, and it would be very, very, very difficult actually to generalize gross categories, because we want to have a broad view and see big categories of signal unit in order to recognize that this is, for instance, a certain pitch, or this is a certain chord, etc. But then taking signal that were downgraded, the differences would be smoothed, and then we would have bigger categories emerging, which was exactly what we were looking for. This was just our intuition, but I don't know at all if this fits with the stochastic resonance theory. But actually, the point is we had to use noised signals. So thank you for the reference.
Good point, because there is another interesting thing that maybe is related, is that I think Xavier Barcelona, he worked with this kind of, well, it's very well known that if you put very pure harmonics to compose a sound, you hear something that is artificial. You have to put some noise to glue them. It's a classical thing about our perception. We will understand the sound as some unique sound and not a superposition of sounds. If you put some noise on frequency, on the value of frequency, that's maybe related. No, noise in the sense that if you put something very perfect, okay, the frequency F0, 2 F0, 3 F0 exact, and you add all this, you hear three sounds generally.
Hello?
But if you make them, then
Hello?
we have a drift along the time. You understand the sound as a unique sound. It's very well known this, and it's the phenomenon of perception. And so maybe it's related with this. But stochastic resonance, there is one point about it that's very important, is that the noise must be in resonance with the signal, in the sense that the point is, since it's very weak, and you put exact the level of noise such that you will detect that will trigger some other thing, And this other thing, you make a mean, like a PWM, you make a mean, and then you rescue the original sign. But you have to have a noise very resonant with the sign. That's why they say stochastic resonance. That's a very important point. But this is very technical, I think.
I want you just to do the microphone. You can speak up.
Grab it. Does this work? Yes. I would like to go back to your early comment about the three dimensions. It sort of strikes me sort of a, how do you call that? The funny coincidence. I talked about Herma, talked about Xenakis, and the text that that accompanies the composition that I talked about, where he explains his model, starts with perception, and he talks about three dimensions. He talks about pitch, duration, and intensity as being the three fundamental ones. So back in the 60s, and talks about timbre as being this sort of very strange thing that you cannot really measure all that well. I mean, it's really exactly the topic. And then he goes on, to compose Herma, where he, I think, tries to several things at once, and this might tie into more generally into music creation and analysis. On the one hand, he tries to compose a work using extremely simple principles. So he got his inspiration from mathematics back then, the simplest structure possible, the one from which you could build all mathematics, at least that was the opinion at the time, that was the dominant view at the time, were sets. So the easiest thing, you take sets of pitches and you work with simple operations on sets. But also, I think something he tried to reach is by increasing the density, by increasing the amount of information to arrive at something that is timbre, that is something that is beyond just the timbre of the piano. Yeah. You get to something and it's something that he worked on his whole career. So this, which actually increases the whole thing with timbre, because you think, well, timbre is an instrument, but no, it's not necessarily with one instrument. You can actually create things that are not, or timbres, let's say, that are not the original sound of the instrument. So these are the two things he uses, or he attempted in this work. There are many other ones, and I think this was quite his intention. But now, did he have, now tying to Adolfo, did he have complete control over what would happen? Probably not, because the piece isn't completely playable for this one thing, and he was an extremely intuitive person. So there's a whole theoretical construction. It's clear that he had a vision of what would happen, that he thought a lot about how he would choose his pitches in his sets and how he would combine things. But of course, he didn't have complete control. And it shows while he was composing, he changed things, he enhanced things, and there it wasn't his rational mind that was working. It was probably making a statement. It was his intuition, sort of. And so, right.
The only thing is to take the microphone to the
exactly.
But Moreno wants to say something.
Can I add some?
Yes, please. Please.
Can I add something about what you're saying? If I remember correctly, in this article in which he's speaking about pitch, loudness, and duration, he says that Xenakis says that actually these three parameters have the same formal structure, which is a ordered set structure, a total order structure. Okay, and that's very yeah, and but we could imagine structures in which you have partial orders and try to kind of generalize a little bit. We know that there is this sieve theoretical approach which is underlined in Xenakis' writings, which captures exactly this unidimensionality with total order. But of course, it comes back to what I showed yesterday, these lattices structures, which are nowadays, I think that very generalized framework in which you can classify structures which do not have this property of total order. So I wonder if maybe we are just forgetting the timbre because we don't have the tool which are the most appropriate, the formal tool, which would be lattices, and this formal concept analysis, for example, as a framework, in order to give to timbre the kind of same characteristics that we can apply to other parameters. Is a simplification, of course, but I think at the same time it goes in the direction of the limitation of the formal approach to music that was asked by Adolf. Is it really true that there is a limitation, or for composition, or simply we don't know so much about the possible generalized structures and the way in which mathematics can grasp, can be so adaptable, so can grasp parts of the realities which nowadays they appear to be just the field of intuition. And I'm not sure that there is really a dichotomy between formal approaches and intuition. I think it's just a matter of the evolution of mathematics, which is probably more and more adaptable to practical situations, and maybe in the future we'll see composers that will work with very flexible mathematical tools which are formal, but which are not constraining the creative process in the way in which probably today is the case. I don't know if you want to add something.
Just a remark about formal and intuition. In general, when you want to show that the compositional process is not totally formal, and this is an example that you took with the constellation, Andromeda and Sirius. In general, you show that if you're trying to impose a certain analytic view on the composition, saying, oh, it is done this way with such and such formal structure, often it happens that if you ask the composer, he said, no, I didn't do it that way. I just did it that way, and then it's a little bit puzzling, and you notice that you could have several different views on a composition and several description and analysis, including the particular one, which is the composer's one, which should be the ground truth, because normally the composer knows, but it's not always the case. Normally, it's not always the case. Knows exactly how he did it. But I have a remark. This is also true in pure mathematics, because for a particular theorem, you could have several different demonstrations, and you could have several different paradigms, mathematical paradigms with different kind of demonstration that would lead to the same truth, to the same result. And still, it's a formal process. It doesn't mean that the mathematical truth that is behind the theorem is something that it completely escapes to our mind. No, it's just that, well, mathematics is also a complex universe with different spaces, different paradigms, different way of looking at things. So the fact that it also happens in composition, the fact that you have different possible view and description, including the one of the composers, doesn't mean doesn't always mean that the composition is completely intuitive just because the composer says so. No, you don't know actually. So I have a story, because I had been working on with several people at IRCAM, including Stefan and Michael Malt and Moreno and other people. We have been working on the notion of modeling musical pieces. It's a little bit weird, because scientists know exactly what is modeling. They know what is a model. They know how you create simulation of a model in order to understand a certain phenomenon. But how can you model a musical composition which is supposed to be something very unique and singular? So no generality about it. It's not a natural phenomenon that you could generalize to, I don't know, like the stars and the celestial mechanics or something. But you can still do it, because there's a shift, there's a paradigm shift between a single composition seen as a very singular point, something that is very unique, to a composition seen as a point that is an instance, an example of a certain neighborhood in a certain space. The space of all composition, of all possible compositions, and specifically maybe the subspace of all composition using the same kind of techniques, formalizations, view, etc. And the piece is a particular point that the composer chose or constructed. But then there is a neighborhood and many, many other pieces that could have existed with the same approach, mindset, way of writing, etc. But it chose one. So when we build a model, we try to actually implement a computational model, computational structure, a program that would be able to generate the neighborhoods of many, many different pieces. And of course, you have to check that it is able to generate the particular piece, which is the real piece, the one that was, signed by the composer. And of course, we did it in collaboration with Stéphane and Moreno and Mireille Lategan. We did it for Herma. So you mentioned Herma and the fact that you could generate different variants of Herma. So we built up this computational model. In this case, it is very easy because the composer gave the recipe in the book. You know more or less to do it. And then you can generate the neighborhood and several pieces that really sound like Herma. They have the same dynamics. They have the same distribution of notes, but in the detail, it's not exactly the same order of notes. So I was talking about modeling pieces because we tried to model a piece by Ligeti, a European composer, who is a composer who was very interested by science. He looked at many things. He was interested in fractal geometry, chaos, complex dynamics, etc. So we formalized a piece. I just don't remember the name. Do you remember? Huh? Melodian, which is a
Melodian, yes. Because I suppose you're talking about the piano concert.
Oh, okay. So it was Melodian. Okay. So with Marc Chemillier, another researcher in Paris, we built up a computer model in using the Patchwork computer language. Patchwork was the ancestor of open music that you saw yesterday. And we built up a model. When you build a model for a piece, you expect to provide it with least possible amount of input data, because if you give it as much data as you have in the score, then you're not building a model. You're just describing the score. But if you're able to have a computational structure and input it very small amount of data, and then it's able to regenerate the piece, then maybe you have understood something about the structure and the dynamics and the systematicity of the piece. So we did it for Melodian, and we had the feeling we had a very neat model, and it would generate the piece, exactly the piece, note by note. We are not inputting too much data, and we think he must have done it this way because it's not possible otherwise. It's not possible that just trying improvising on the piano and generating the piece. You get something which is absolutely equivalent to this computer program, which is a very, very compact model. And then one day Ligeti comes at IRCAM because they were playing the piano concerto. They were rehearsing in the
because it's also connected to Mandelbrot.
Yeah, this one, yes. Yeah. So they were rehearsing in the IRCAM concert hall, and Ligeti, he's a star, he was a star. Now he's dead, so we were younger at the time, and a little bit shy. So we went to say, Master, can we show you our little model? So he's very nice, and he comes to the office, and we show it on the computer, and say, oh, that's great, that's very interesting. I didn't do it that way at all. But he says something. So we were, but he said something very nice. But he said, "But you are absolutely right. What you did is it's the truth. It's not it's not rubbish. You're right. I mean, what you show is true. There is this structure inside. I did it another way. But sometimes you have several ways of building a complex structure, and you can describe it in different paradigms. But nonetheless, the structure is here, and it's interesting, and it teaches us something. This is just.
So we're talking about computer mod. Maybe Jean wants to say something about it. You have been working on that.
Actually, I had in mind something else about the previous topic about timbre perception and more from the point of view of creation. because when I did my PhD, the topic was about writing sounds and composing sounds. So that's kind of related with the things I have shown yesterday afternoon. And we had this problem of what are the right parameters to propose to composers to make sounds with sound synthesis. So we carried out a number of interviews with composers, and we tried to see what existed as tools, as practices. And there was this book about timbre by Jean-Baptiste Barrière and all other people in the 80s published. It was a big discussion about what's timbre, how can we write timbre, and how do we pursue. I think there was no answer at the end, and the only answer was timbre is special. It's not the same as the other parameters, so we cannot do very much about it, and it remains kind of one of the mysteries of sound creation and perception. And so at the end, the question of how to determine timbre with parameters was kind of not a question, and there were so many ways of synthesizing sounds with all the techniques that trying to find the correct set of parameters, unidimensional parameters that you can represent on a score and notate and everything for composition was also not a question we could answer. There was also lots of work on descriptors, but it's more from the point of view of perception and analysis. And all the works carried out was not really very much reversible, in the sense you could not take a set of descriptors and regenerate a sound with these descriptors. At much, the best they could do was transform a sound according to a given descriptor to make it more bright, more something. But no, to my knowledge, there is no way to synthesize a sound according to a given set of descriptors. So the result of all this is we came back to the same idea that I think drove the idea of computer-aided composition when all this patchwork and open music environment were developed, was to propose to composers the way to program themselves the process that would lead to the sound they have in mind. So I think there is I didn't follow exactly how you came from the intention problem. Yes, you said that first to the question of timbre, but we kind of did the reverse path and say, okay, because we consider programs as being kind of an intentional representation of a musical structure. If you have a score and you have the program that generates the score, so we prefer focusing on this program that generates the score because it represents the intention, and as Gerard said, it can be modified, you can develop it in a different way, you can change something and lead to a new structure. So at the end of the work I did in the PhD was more like following this idea and say, okay, we focus on the intentional representation when creating sounds, so we mostly propose programming tools that allow to access the maximum possibilities of existing DSP techniques. And so that was kind of the answer to the question of how to write timbre, how to create timbre. It was with this intentional representation that the compositional process is when represented in a programming environment like open music in this case. So and it's kind of the the other way.
May I say one thing? When I said the intention, the relation between the intention and timbre, what I say is not in the point of view of composition. Finally, it will be the point of view of composition, but and before this, I mean, when you make an interval, you have an intention to do it. You manipulate one parameter, that is pitch. Now, suppose you have another parameter that has the same qualities I said. You could have the intention to manipulate it and produce a musical effect. That's all. And then you put this in a big composition framework after. That's in this sense I was saying. I would like to say another thing also is sound is not very difficult to characterize or to model. I mean, as an audio designer, we have thousands of tools to make this. It's really something very easy finally, of the mathematical point of view. However, what is very complicated is the perception. That's all. We really do not know how the brain works. And that's why this is difficult. For example, you may have very different signals that produce the same effect. So I think the main problem is how to model. For example, you said about the model with very few parameters that would model something very complex. That's the holy grail of synthesis. It means something that FM did somehow. Very few parameters, you can obtain a very rich set of possible sounds. For example, see what a DX7 made in 80s, something like this. But that does not solve the problem. I mean,
to predict
yes,
what
yes.
sound
The problem is you may produce very different sounds, and they have the same perception. For example, if you change phases, the phase of the spectrum, you change almost nothing. However, the signal, if you see it, they're different. If you find a norm to calculate the difference, big difference. So what would be the norm to decide that a sound is produce the same perception? I think the big deal, for my opinion, is perception, because sound is easy.
Also, the composer has a musical background and experience. Well, maybe not very much, but they will get more and more experienced when they use sound synthesis. And that's the same thing as writing music. You cannot predict what will be the effect if you're not a skilled composer. So you can write whatever, but if you're a good composer, you know what you're writing and what's going to be the musical. I think for sound, it's comparable too, because it's not the point of making synthesis easy. It's just to be able to predict when you do something about sound synthesis, what kind of result you will get. And that's also with everyday work and training and practice.
Yes. So, for example, Stefan said that Xenakis in some point in the composition, he was dealing with timbre. Fine. He was making something transcendental of the time of the piano by his composition. I think that's not for the weeks to do this. I mean, to make a different timbre with the manipulation of other things.
Sort of, I don't know if it's really directly connected, but I kind of like this parallel that we have between sound synthesis and sound and composition of work, in the sense that the complexity of having sort of this mapping between the generation, the result, the perception, and the possibility you have also to perceive a result. So a sound, for example, you can synthesize in various ways, and a composition you can also consider in various ways, not necessarily if you have a 12-tone composition, the intention of the composer, of course, was to use a 12-tone row, and you can check if he used it consistently, but through the composition he will create all sorts of other structures that sort of emerge, or that he intended or did not intend. And so this whole richness that comes out of the structure that is the composition, or the result of the creative process. I don't know whether you sort of agree or think that I'm completely that there's sort of this parallel that between the control, the attempt to control something, where you have a set of rules that as a creator you give yourself, and that you follow more or less, and you get to a result, and what it becomes afterward in the world, and when you try to reproduce it or to understand it, how extremely unstable it becomes, and how you can perceive it or see it or analyze it in different ways, which is sort of also where the whole creative aspect comes, where analysis, looking at the composition, for example, someone analyzes it, sees a structure that might not at all be the composer's, but might inspire him, to him or her to do something similar, different, that might be in the neighborhood of the score or not. It's sort of, I don't know, an interesting sort of parallel.
So maybe we have to go to an end, but do we have questions at the internet? Is anybody has a question here for the table? Okay.
Por favor.
It's something about Almeida Prado, and I think that we have in a composition two main moments. The moment when the composer have an extra musical stimulus, and the second moment is when he puts it in a paper or record it, and you have a product that is based on musical processes that he learned. So the analyst or the performer learned in that universe too. And it's possible to understand that product, that having some intuition, but your this intuition have a limit of different variations. So it's possible to understand this moment of the transition of the motivation to the music. It's one moment, it's very difficult to understand, but understand that music that was generated, it's very possible, I think. And then two moments. And about celestial shard, and the composers have a charm of this, to when they said, oh, I feel that, but when they are working, they work with elements that we know. Think that.
Okay.
My comment about what you said is the following. There is a French mathematician named Henri Poincaré. Poincaré wrote a paper about the mathematical creativity, and he said in this paper that how he discovered so much beautiful mathematics. And there's no logic for that. And he said, for example, he was interested in something very difficult, maybe automorphic functions. And he studied a lot and discovered nothing. But he was a kind of engineer also, mathematics and engineer. And so he had a problem in a city with something in engineering, and he went there by horse. And when he finished, he felt, okay, I have to ride my horse again. When he stepped to ride the horse, instantaneously, the solution came to his mind. So, no, not the horse. So it's his mind.
The off horse. Off horse. It's off horse.
Off horse, yes. The horse has nothing to do. But maybe.
Off horse.
So a horse can be very important in your. But that's what happened. Almeida Prado and Poincaré had a lot of patterns in their heads. This is a kind of volcano. Sometimes goes in eruption, but the structure is that. That's why I said that the human brain, it's very plastic, very these things that we know. I am a mathematician. Are very. We are in the beach. There's an ocean there. We are in the beach, and we are stepping, walking by the beach all the time. Sometimes we go a little bit more into the sea, but I think that this kind of music intuition is far beyond what you do with formalized music. In this sense, I am provocative because Xenax was a mathematician also. But in my mind, I can say that I think that Xenax was more composer than mathematician, far more composer than. So he wrote formalized music just to a glimpse for us. So you can use it like.
Yeah. So.
Okay, we have to finish. Unfortunately, maybe if anybody here, or inside or outside, or there at the internet wants to say something, there's a question. No, no questions. Who? Andre? There's somebody asking a question, Tatiana. Okay. Okay.
Considering the new approaches as innative or externalist theories of perception and cognition, someone in the table think that may brings a new set of principles for music analysis and composition in what terms?
Embodied mind. The concept of externalism and embodied mind. He asked you if there anybody that's something to comment. And a musical analysis.
Yeah,
Okay, let me answer this way. Yeah, tomorrow, Andrea, I know you, so I'm very glad you asked this question. Maybe tomorrow we're gonna introduce this discussion. It's something I'm gonna put on table tomorrow. Okay, I'm sorry though. Maybe it's better to develop this subject tomorrow. Okay, and is anybody wants to say anything else? Cool. I think worked, and we are on 1 hour. Really 1 hour run discussion. Thank you very much. And I guess it worked, so we can have this nice dialogue. Thank you all, and we see each other at 2 o'clock this afternoon. Okay, bye.